Picture the edge of our solar system. Scientists thought they had it mapped, modeled, and understood. Voyager 2 just proved them wrong. A probe launched nearly 50 years ago crossed that boundary and sent back data nobody expected, revealing that the line between our solar system and interstellar space is nothing like the textbook said. Think of the sun as a giant X-ling machine. Every second it breathes out a constant stream of charged particles, the solar wind, radiating outward in every direction at hundreds of miles per second. For billions of miles, that wind dominates everything around it. It shapes the space our planets live in. It pushes back against the rest of the galaxy. But eventually, far enough out, it runs out of force. The pressure from interstellar space, the gas and magnetic fields drifting between the stars, finally overwhelms it. The solar wind slows, stalls, and stops. That stopping point has a name, the heliopause. And the heliopause isn't just a scientific boundary on a diagram, it's the actual edge of our solar system. Cross it, and you're no longer in the sun's territory. You're in interstellar space. For decades, the models were clear on what that boundary should look like. Scientists expected a relatively smooth, consistent shell, like a bubble blown around the sun, roughly uniform in all directions. The solar wind pushes out, interstellar pressure pushes in, and they meet at a stable, well-defined line. Clean, predictable, a shoreline you could map. Then Voyager 2 crossed it, and the shoreline wasn't there. What Voyager 2 measured when it punched through the heliopause in late 2018 didn't match the model. The plasma readings, measurements of the charged particle environment, were denser than expected on the interstellar side. The magnetic field at the boundary didn't behave the way simulations said it would. And here's the detail that quietly broke everything. The boundary itself was thinner than what Voyager 1 had measured when it crossed more than 6 years earlier, in a different location. That comparison is where the real discovery lives. You'd expect two probes crossing the same shell, even from different directions, to report roughly the same thickness, the same structure, the same basic physics. They didn't. Voyager 1's crossing looked one way. Voyager 2's crossing looked meaningfully different. Same boundary, different location, different data. And that gap between the two readings isn't measurement error. It's information. It's telling you the boundary itself is not uniform. Think of it this way. You're expecting a clean, even coastline, the kind you draw on a map with a single smooth curve. What you actually find when you get there is a jagged, uneven edge, rocky in some places, flat in others, pushed inward on one side, bulging outward on another. That's what the two Voyager datasets, taken together, reveal about the heliopause. It's asymmetric. It's dynamic. It may be rippling or compressed on one side by the pressure of interstellar material flowing past, the way a soap bubble deforms when you blow on it from one direction. That asymmetry isn't just interesting. It's structurally important. The entire reason scientists care about the heliopause is that it functions as a shield. The sun's bubble deflects a significant portion of galactic cosmic radiation, high-energy particles streaming in from the rest of the galaxy, before it reaches the inner solar system. Earth's magnetic field handles a lot, but the heliosphere is the first line of defense. If that shield is uneven, if it's thinner or weaker on one side than the models assumed, then the protection it offers is also uneven. And every calculation built on the assumption of a uniform shield, including radiation exposure models, for future missions pushing beyond Mars, was built on a picture that Voyager 2 just complicated. The boundary between our solar system and the rest of the galaxy is stranger, less predictable, and far more dynamic than anyone planned for. That changes the math on what's out there, and on what it means to travel through it. If the heliopause turned out to be asymmetric and uneven, rather than the smooth, uniform bubble scientists expected, does that change how you think about deep space travel being viable? Drop your answer in the comments below. Now let's talk about what this actually means for missions beyond our solar system. This isn't just a discovery about one probe crossing one edge. Both Voyagers are now outside the heliosphere, in a region known as interstellar space, the space between stars. That makes Voyager 2 something genuinely unprecedented. The only instrument humanity has ever placed in interstellar space that carried a working plasma sensor. The first to directly measure the plasma of the interstellar medium, before that instrument was shut down in 2024 to conserve power. Every number it sends back is a first. There is no other data set to compare it to, which means when those numbers don't match the model, you can't blame the instrument. The model is wrong. And the model being wrong has a very specific consequence that isn't abstract at all. Voyager data has shown that the heliosphere deflects a significant portion of galactic cosmic radiation. Estimates from the scientific literature, drawing on Voyager measurements, suggest roughly 75 to 80% of cosmic rays in certain energy ranges are blocked before reaching the inner solar system. That's not a background detail. That's the number radiation engineers have been working with for decades. 70% filtered out before it even reaches the inner solar system. But that figure was calculated on the assumption of a relatively uniform, predictable bubble. The standard model of a smooth static heliopause is no longer acceptable. Scientists now have to account for inhomogeneities, oscillations, and permeable barriers. If the shield has weak points, if it's thinner or more porous on one side than the other, then that 70% figure isn't a constant. It's an average, and averages hide the outliers that actually matter when you're planning a crewed mission. Any mission pushing humans beyond Mars and out toward the deeper solar system is operating in an environment where the radiation math just got more complicated. Knowing how interstellar particles flow into or are scattered by. The sun's bubble is now critical for forecasting cosmic radiation exposure for future missions. The models that underpinned earlier mission planning were built on the old picture. That picture has been revised. Not scrapped, revised. But the revision matters because in deep space, the difference between an accurate radiation model and an optimistic one isn't academic. It's biological. The implications don't stop at our solar system's edge. The heliosphere inflated by our solar wind is the direct analog to astrospheres inflated by the stellar winds of other stars. Every star with a solar wind, which is most of them, has its own version of this bubble, its own heliopause, its own boundary between its territory and the interstellar medium pressing in. Before Voyager 2, astronomers were modeling those astrospheres almost entirely from the outside, inferring their structure from indirect observations. Now there's a ground truth, a physical measurement taken in situ of what this boundary actually looks like up close. Both Voyager probes have demonstrated that the heliopause is a highly non-uniform, porous boundary between the heliosphere and interstellar space, and that finding becomes a template. If our boundary is dynamic and asymmetric, the boundaries around other stars probably are too. That changes how astronomers think about the radiation environments of distant planetary systems, including ones that might host life. Through all of this, the revised models, the radiation recalculations, the new framework for understanding stellar environments across the galaxy. The instrument responsible is a spacecraft launched in 1977, running on a power supply that has been slowly dimming for nearly 5 decades, transmitting data across billions of miles at a signal so faint, it takes specialized antennas just to hear it. A probe whose transmitter draws roughly the power of a household light bulb just handed 21st century science one of its most important data corrections. The edge of our solar system turned out to be stranger, more dynamic, and more consequential than anyone planned for. And we only know that because something we built almost 50 years ago was still listening when it got there. Subscribe for more on what space exploration keeps revealing. And watch this one next.